I just wanted to mute my event Mobi because I think you start getting feedback and all sorts of weird things happen. So, okay, I guess we're on time here. So, welcome everybody to the I guess the second session of severe and extreme convective storms, detection, prediction, climatology in the future, part 2. So we have about 6 speakers lined up. Connell Miller will go first. And yeah, so I just wanted to, Eric von Lochem, second presenter, Dave Sills, third, Daniel Butt, Lesley, Elliott, and then Bradley Power go last. So yeah, so I think we're all set to go. Everybody knows the timeline. So I guess, Connell, if you want to share your screen, we can begin with your talk.
All good there, John?
It looks good to me.
Okay, great. I'm just going to move some of these video panels and meeting controls out of the way so I can see my screen. Alrighty, good afternoon, everybody. My name is Dr. Connell Miller. I'm an engineering researcher with the Northern Tornadoes Project, and along with my co-authors Greg Cobb and Dave Sills, here to talk to you today about the assessments of wind speeds for the Didsbury, Alberta EF4 tornado on July 1st, 2023. The next talk talks a bit about the actual tornado and the meteorology itself, so this talk is really focused on the engineering aspects of the event. If you've never heard of the Northern Tornadoes Project before, just a brief overview here. We like to call ourselves a severe weather community endeavor. Our core team is comprised of both meteorologists and wind engineers, of which I'm on the wind engineering side. And we also have an external research team focused on longer term improvements. We have strategic partnerships with the University of Manitoba, the Weather Network, Instant Weather, CatIQ, as well as a close collaboration with Environment Canada. And our main goal is to advance knowledge of true tornado occurrence and risk across Canada. So the two main goals or tenets of that, I suppose, are the detection, the assessment, the documentation, and the public access of this data. And this is for a few reasons: for climatology, for risk assessment, as well as eventually taking a look to the effects of climate change, which I believe Dave is talking about a bit later. And then finally, research to improve event detection, assessment, and prediction. So when the Didsbury event happened and we realized some of the extensive damage, the Northern Tornadoes Project sent out their own survey team, and we collaborated with Environment Canada to assess this event. So we had a team of 5 for ourselves, and then Jesse, Heather, and Justin from Environment Canada, who was also there in collaboration with us. So this is, we'll just jump straight into the damage and taking a look at the event map itself. So the Didsbury, Alberta tornado, it was rated an EF4, 275 kilometers per hour, due to all walls collapsing on a 1 or 2 family residence, which we'll discuss a bit further later. Had an overall path length of 15.3 kilometers and a max path width of 620 meters. And thankfully, only 1 injury and 0 fatalities. I attribute a lot of that to the warning getting out of there ahead of time before the worst of the tornado went through. So super glad to see those numbers so low. So why is this event map important? Well, tornado damage is cleaned up quickly, meaning there's a short time frame to analyze this data, leading to the need to create a virtual representation of the damage so research can be done in the future. This is mostly because we don't know the research questions until long after the survey is over, so it's good to archive this data so we can go back and do analysis on it later. So there's 2 main uses for the event map. Number 1, operationally, to assist with the EF scale rating of this event. And number 2, to archive data that can be used for research projects in the future. So this presentation is actually going to go over both for this event. The main area we're going to focus on is sort of near the center of the length of the tornado. Definitely the worst properties that were damaged here. I just called them the Highway 2A properties. This is a Google satellite view from May of 2023, so just 2 months before the tornado occurred. And here is the mapping that we did with our drones to show the extent of the damage on this one property here. And there's quite a lot here. 3 homes, with number 3 being rated as the EF4. I've labeled them 1, 2, and 3 because we're going to come back to them later. 11 barns and outbuildings, 4 grain silos, 1 mobile home, and a long list of vehicles, farm equipment, and trees. We actually went back and mapped it again a month later just to see how the damage had changed. And later mapping showed that all the residences and structures on these properties were condemned and demolished. So even though not every single piece of structures was experienced EF4 level damage, all of them experienced damage significant enough to warrant the condemnation of all the buildings. So going back to these homes, so this is the home on the eastern side of the Highway 2A there. So what you're looking at here is the center photo is the top-down view from the drone that's pointed north. And then you can see where there's arrows is sort of the view from the ground at that angle there. So a couple interesting things about this building. Again, this was right beside the or not quite right beside, but just across the road from the building that experienced 275 kilometers an hour. But there's a couple reasons why this was rated on a lower bound here. Number one, you can see there's some interesting construction going on with the roofing itself. So usually you don't want to install your metal roof directly onto your shingles. Usually there's battens if you do go that route. So obviously we had some concerns there. And then our main concern was that what you're seeing here is an out-of-sequence failure. So usually when you're taking a look at tornado damage, you expect the roof to blow off and then the walls to fall down, not the walls to fall down before the roof blows off. So we were looking for signs and signals of like, okay, were any of the windows blown out? Were the door open? Was anything like that going on? But when we started taking a look at the structural connections of the top of the wall itself, and I don't know how well this comes across on the Zoom or not, but the nailing through here seemed very haphazard and also just not the correct size, length, or patterning that you'd expect from a roof joist to a wall joist. So that's why this ended up being rated as a lower bound building. Secondly, this is the home that was directly beside the house that experienced 275 kilometers an hour. This one mostly seemed to be built up to code and to have proper construction. Just interesting to note that in the southeast corner, it appears to have been impacted by some sort of object, probably one of the cars or other farm equipment that were being thrown around, which we'll talk about a bit later. And then finally here is home number 3. This is the reason why this tornado was rated as an EF4. There's me standing there pondering what's going on with these foundations and other structural connections there. So again, looking at it, it all really came down to the foundations here, right? If the strength of the foundations connecting it to the wall weren't adequate, we wouldn't have been able to rate this as an EF4 event. However, what we did is we actually went to the Alberta Building Code and just made sure that the foundations were up to code. So going through it really briefly here, you can see that it does allow for embedding in concrete, which is what you're seeing on the right-hand picture there. 2 sill plates placed on edge and separated by blocking. So that's all good there. And then it does give some other caveats here in terms of, well, if it's a building with 2 or more floors, you can't do this, but it was just a single-story building, so that's fine. And then it does give some caveats that if it's in an area with significant seismic activity or significant wind pressures and things like that, you can't do this as well. But this house was not in this area. So according to the Alberta Building Code, the 2019 version, this was completely built up to code, and it was a relatively new building, which is why it received the expected value of 275 kilometers per hour. So that's the event map as operational uses, right? So let's talk a bit about the research uses. If you go back to this drone imagery here, you can see there's a couple other interesting things. There's 7 trailers that were thrown, 4 tractors, 3 vehicles, and this is sort of what that looks like on the ground, just absolute chaos. And focusing in a bit on this one here, it's quite the significant piece of machinery, weighing over 10,000 kilograms. And we believe it was actually thrown in the tornado based off this imagery, 85 to 95 meters. We know it started there because of homeowner recollection as well as satellite view from the historical there. And looking around that area, it doesn't look like there's any markings that would suggest that this thing was dragged or sort of just rolled over here. So we believe it was fully lofted into the air. So how do you model a large object flying in a tornado? Well, you can take complicated tornado equations, complicated debris equations, and use a Monte Carlo simulation to use random variables and try to find 10,000 trajectories that match the approximate trajectory of what was observed in this event map here. And what we see from that, so because we simulated 10,000 times, we can actually generate a graph that shows the probability of lofting for the combine itself. And you can see, while there is a small chance that this lofted in that EF4 range, it is a considerably likely scenario that this could have potentially been an EF5 event. Now, we're not suggesting that this should be upgraded to an EF5 event. What we are suggesting is that we need to continue to develop tools like this to create the most accurate assessment possible. And if anyone is interested more in this, we actually looked at a lot of different debris trajectories in events like the Didsbury tornado, the Elliott tornado, the Scarth tornado. It's open access, so anyone can feel free to download and read that if you want more. So a few quick takeaways, because I believe I'm out of time. Obviously, this tornado enters some rarefied territory among Canadian tornado events, including being the strongest tornado since the Edmonton Black Friday tornado, and only the second one to be rated EF4 since we switched over in 2013. The high quality data that's captured by NTP is allowing us to create an archive of areas that have experienced severe natural disasters for ongoing research, and we need more methods for determining wind speeds in tornadoes. So 2 quick links here. If you're interested in seeing the event map for yourself, there's a QR code for that. And if you're interested in the debris trajectory paper, there's a link for that as well. But happy to take any questions if anyone has any.
Yeah, thanks very much, Connell. Very, very interesting. Let's see. I'm looking for questions. I do not see any questions online. I don't know if anybody else on the Zoom panel here has questions for Connell. Any of the Western folks kind of critique Connell's work? Okay, and I'm not quite sure if we started maybe a little bit early. I have 2 timelines here, and I'm not sure which one's correct. But anyways, we should.
Oh wow! Okay, I thought it was 2:05 was supposed to start, but
yeah, well, that's what I thought too. And then I was told we have 5 minutes to do intro or something, so I'm not quite sure. Anyway,
okay, is what it is.
It is what it is. So in terms of the, so I just had a quick question for you, Connell. In the plot that you showed for lofting, lofting probability. So those are obviously, theoretical values, right?
Sure. Yeah.
So maybe the winds that were produced, maybe they were sufficient to do the lofting as opposed to the theoretical value that seems to be maybe a little bit higher. So is there anything like aerodynamic wise? I guess the aerodynamics of these objects, I don't know how you take that into account.
Yeah, so there's 2 sort of thoughts behind that. So the line that you were seeing, that was the dash line. That was just like the traditional EF scale rating of that event. That was at 275 kilometers an hour. And then our cumulative probability graph there for what the lofting could actually be. So there's either 2 things going on there. Number one, there's been research that's shown that we have the tendency to underestimate severe tornadoes like EF4, EF5, just due to the fact that the EF scale is a damage-based scale. So we require things to be damaged to be able to get an accurate assessment of them, which isn't always the case. And then secondly, it could be the fact that the debris initialization part of that is very complicated. So the vertical winds to loft things like cars and combines are very complicated to determine, and I don't think it's been fully resolved yet. We're very confident in the method itself and the Monte Carlo simulation and using this, but hopefully as tornado, like analytical tornado models and that debris initialization question gets solved better, we can continue to just add that into the model and improve it.
Mm. So does your model actually include vertical velocity wind, like the upward?
Yes, it does. Yes,
Okay.
it does. I don't know if I 100% believe it, but it's using the Baker and Sterling model for tornadoes, which is radial, circumferential, and vertical velocities.
Okay. Interesting. Okay. So we actually
Yeah,
do have
so it does actually take into account the trajectory, right? It's not just like this is the wind speed to get it off the ground. This is the wind speed to get it off the ground in 100 meters that way.
right. Yeah. No, that's
Yeah.
cool. Okay. So we actually do have a question here. So do you see any significant ground scouring purely due to the wind in this event? Did you guys see any ground scouring?
Oh, absolutely, yeah. I didn't really have much time to go over it, but even in that last picture, you could see just black going through the ground scouring there. We actually have a grad student here that's looking at NDVI vegetation indices, which gives you a bit of like the plant health and the ground health and how that decreases. And the area just east of where I showed you lights up like a Christmas tree, for lack of a better word.
Interesting.
Yeah.
Yeah, I guess just sort of follow on to the scouring. I'm not sure. I wasn't there in person, so I don't know what it actually went over. I know in some cases there's been pavement that's been, stripped off the surface. So I don't know if you guys found that or not.
No, we didn't quite find that level. It seems like the ground scouring got worse, like at its peak in the middle of a canola field. So I didn't see any pavement that had been scoured in that way.
Okay.
Yeah.
Good. Okay, well, thanks very much. That was very good talk. So I guess we can move on. I guess Eric Van Lochem is next. So Eric, you can start sharing your screen. So Eric's talk is called Synoptic Scale Patterns Associated with the Didsbury, Alberta Tornado of July 1st, 2023. So this will be interesting to see a follow-on to Connell's discussion.
Perfect. Thank you very much, John. Hopefully everyone can see my screen here.
Yeah, we're good to go.
Okay, excellent. So we'll get started then. Yeah, so John introduced me there. My name is Eric Van Lochem, and I am an operational meteorologist with Environment and Climate Change Canada in Edmonton, Alberta. And I was on duty for this event last summer, and I'll start by saying it was the most challenging and probably the most rewarding day of my career so far. So let's get right into it. Certainly, it was a remarkable tornado in a number of ways. The intensity probably being the factor we're all most familiar with, only the third violent tornado in the history of the province of Alberta. On top of that, the timing of this tornado was somewhat interesting in the sense that usually when we talk about tornadoes of this intensity, they tend to occur more around kind of that 5 to 6 p.m. time frame, supercell tornadoes on the Canadian prairies. In this case, only 5 significant tornadoes over the last 45 or so years have occurred any earlier than Didsbury, which was at 1:45 p.m. in the afternoon. And as well, so violent tornadoes in Canada, obviously they're pretty rare. We've only had about 20 or so over the last 250 or so years. And less than a quarter of those had no deaths. So it's usually these violent tornadoes that result in a disproportionate number of fatalities. And in this case, Didsbury, it enters this territory in part because of the Alert Ready system doing exactly what it was intended to do. So let's dig into what happened on July 1st. So we'll start early in the morning, 250 millibars. I drew this upper air analysis shortly after arriving on my shift at 7 a.m. So the main feature you probably want to note here is that negatively tilted upper trough with a deep closed low over the Alaska Panhandle that's arcing into Alberta from northern BC. As well, we have an 80 knot jet rounding the base of that trough, nosing in into Alberta as well. We skipped down to 850. Again, drew this shortly after coming onto my shift. So it's kind of a few features here of note. One is the moist tongue, which you see in the squiggly green line, arcing back towards the northwest into Alberta from the northern Great Plains. And to the north of that moist tongue is cooler, moist kind of flow coming into central Alberta, that 20 knot flow. And then to the south of it, this will become important later. We have hot, dry southeast flow coming in from Montana and drought-stricken portions of southeastern Alberta, southwestern Saskatchewan. And of course, 15 knots coming across the Rockies, and that manifested as a dry line to the lee of the Alberta Rockies. And at the surface, we had a low that morning, surface low developing southern Alberta in the vicinity of Lethbridge, Medicine Hat. That would push northeast throughout the day to lie somewhere in western Saskatchewan by afternoon. This system would drag a cold front back towards the southwest, and that would terminate in the Alberta foothills to the north of Calgary. So we'll take a quick look at some model guidance here. Now we're moving out of real data into model land. So the 12 Zulu regional model at T plus 7 hours. So this is 19 Zulu or 1 p.m. local time. Basically showing ML capes on the order of 1,500 to 2,000 joules. Bulk wind difference values in the bottom 6 kilometers, about 40 or so knots. Pretty typical site for Alberta in July. Would suggest supercells coming off of the foothills, but it begs the question, will they be tornadic? For what it's worth, most of the model guidance, including the regional model, most of the Canadian models for that matter, actually had the area in question to the north of Calgary as being completely capped. And one notable exception to this was the 3 kilometer NAM model, which is a convective allowing model. There's some interesting features here where it's basically uncapped. We have some pretty decent cape and some nice convergence as well. We'll look at this area in particular in the next slide. But the reason I zeroed in on this area is you can see the cape is, it's kind of looks like it's being squeezed, almost like toothpaste coming out of a tube. And what's going on there is this is basically the intersection of that slow-moving cold front from the low in Saskatchewan and a bulging dry line moving off of the foothills to the south of Calgary. So we'll look at a forecast sounding from that exact spot in the next slide. So if you're looking for tornadoes, there's a few red flags here, namely, we have mixed layer LCLs below 1,000 meters, 0 to 1 kilometer shear north of 10 knots. Really nice kind of looping hodograph there. It looks like a, sort of a classic sickle shape. And temperature dew point spreads are pretty low as well. And if you're curious as to where I pulled this sounding from, basically just north of Crossfield off of Highway 2. That's about 10 miles to the southeast of where the tornado actually occurred. And the main reason I wanted to talk about this slide, something called the sounding analog system. So if you've ever looked at a Sharpie-based sounding, you've probably seen a list of dates at the bottom, just like here. These 4 dates are all what are known as like quality matches for significant tornadoes. And this is what the SARS does. So it basically looks at this set of parameters, and based on historical soundings, it tries to approximate a match. So you have loose matches and you have quality matches being a very close facsimile. So these 4 dates were close matches for significant tornadoes. And this is a quick summary of those dates. So 2 of them involved a quasi-stationary front and a dry line, and both of them produced F3, F4 tornadoes. And in the other case, other two cases on the right, Minnesota, Iowa, slow-moving cold front and a weak mesolow associated. And in that case, they were also fairly localized outbreaks as well. We're not talking like multi-state or anything like that, limited to a portion of one US state. And these were the same types of features that would go on to produce the Didsbury tornado last summer. But why don't we look at another case a little closer to home that might have some parallels with Didsbury, and that was Pine Lake, Alberta, in the summer of 2000. I was 11 years old at that time, and I still remember this on the news. So it was a rain-wrapped tornado that hit a campground, central Alberta. 12 people were killed. It was still one of the deadliest tornadoes in Canadian history. And one of the reasons I wanted to talk about this is the similarities with Didsbury. So in both cases, we had an isolated supercell, produced one single intense tornado. That storm occurred near the intersection of a slow-moving cold front and a dry line. The outcome hinged heavily on mesoscale features that weren't well modeled. And there was also a drought over southeastern Alberta. We'll talk more about this later. There were some differences as well, but they were relatively minor. One of the fortunate things is the Didsbury tornado was highly visible, whereas Pine Lake was rain-wrapped. So if we go back to the surface pattern on July 14th, 2000 at 3 p.m. in the afternoon, things hadn't really changed much that afternoon, but you'll see some similarities here where we have a QS front arcing through southern Alberta to the north of Calgary. And on either side of it, we basically have a 15-degree difference in dew points despite a relatively weak surface flow. And, we have cool, moist air to the north and hot, dry air to the south. And the flow based on this map alone would help tighten up that gradient just to the north of Calgary. And then if we look at Didsbury from last summer, so this is at 2:30 p.m. local time, so the tornado was in progress at this point. There we have our cold front, slow-moving cold front with thunderstorms breaking out along it, and then a dry line pushing towards the north, and the storm was basically right at the intersection point of those two features. Again, between Red Deer and Calgary, we're talking 15-degree difference in dew points, and it begs the question, as to why, because that's only 100 kilometers, and we have relatively modest surface flow. And a lot of this comes down to soil moisture and evapotranspiration. So in the summer of 2000, southeastern Alberta was in a severe drought, and soil moisture levels over southeastern portions of that province were pretty much nil, compared with almost totally saturated in west central Alberta. And in a paper written about 20 years ago, researcher Jeff Strong suggested that this contrast between the wet and dry areas basically created a semi-permanent dryline bulge in the vicinity of where the storm occurred, at least semi-permanent in the context of that summer. And this feature served to enhance the severity of the Pine Lake storm. Then if we fast forward to the summer of 2023, so this is the month before the tornado, June 23, areas of west central Alberta had received roughly 2 to 3 times the normal rainfall for that month. And then if we contrast that with southeastern Alberta, it had received less than a quarter of its normal rainfall for that same month. And kind of like in Pine Lake, the Didsbury storm developed roughly halfway in between Calgary and Red Deer, just a little bit to the west, kind of right on the boundary of that transition zone between the wet and dry areas. And as we discussed earlier in the presentation, the airflows on either side of that moist tongue would serve to kind of reinforce this gradient with that hot, dry southerly flow and then cool, moist northeast flow in the wet area. And finally, the last piece of this whole puzzle, this is a composite map at 500 millibars, the wind pattern of all median tornado events on the Canadian prairie. So a median tornado event, statistically speaking, is basically an F0 or an EF0. And this is 340 dates between 1979 and 2020. So these weakly tornadic or non-tornadic outcomes are typically associated with positively tilted troughs and just a generally more progressive pattern in general. And then if we contrast this with top percentile events, so 99th percentile, these are your Pine Lakes, your Edmontons in 1987. There were 9 dates here, all between 1982 and the year 2000. And I should note that this plot does not include Didsbury. So aside from the jet being far stronger than in the previous slide, it's generally just more amplified in general, and the trough has a strong negative tilt to it. And that suggests that there may be a strong correlation between trough tilts and the probability of tornadoes on any given severe weather day in this part of the country. So that pretty much wraps up my presentation. I'll take any questions or comments if anyone has any.
Thank you, Eric. Very interesting analysis.
Thanks.
Yeah, so there are a couple questions. I guess yeah, we should be good for questions. Let's see, there's a couple of them here. So one is, how did the, I guess Environment Canada NWP models do with the Didsbury tornado event? How did they factor into the alerting decisions on that day? I guess you were the forecaster for that day, so you might have some insight into that.
Yeah, so it's actually interesting because I did this talk as well about a month ago. This was kind of the abridged version with my colleagues at Environment Canada. And one of the things I found out right away was that the HRDPS and the regional basically had the area in question completely capped. And that front that I discussed earlier from the low in Saskatchewan slowly, it almost stalled out. But most of the guidance and even some of the earlier runs of the 3-kilometer NAM model, obviously I showed a 12 Zulu run, but the earlier runs like the 6 and the 0 all had that front actually, sliding south reasonably quickly. And the American guidance had actually shown some convection breaking out in the area where the tornado occurred, but had it in the early morning as the front went through. And that was maybe part of the reason why that guidance had the area capped for the afternoon. But the Canadian guidance was capped almost the whole way through. And it had a bit of convection in the morning as well, so that was probably part of it. But I guess in a nutshell, model guidance, if you were kind of living and dying by model guidance, you would have missed this event. A lot of it came down to pattern recognition. And if you were familiar with Pine Lake, as I was when I came in, I was immediately worried about what was going to happen that day. And a lot of it came down to that pattern recognition. But that stuff's not obvious. It's not obvious at the time. And if all you're looking at is model guidance, it makes it really tough.
Yeah, I hear you. Yeah, I mean, some forecasters, well, some of the more seasoned forecasters will say this might be one of the largest events you get to see on the desk for many years to come. So it's
for
kind of unusual to see that early in your career like that. So it's kind of interesting. Another question. I was struck by how you used the edge of the NAM to look for the squirting toothpaste cape signature. How much faith do you and other forecasters put on model outputs at the edge of the model domain?
So that's a great question. And I didn't look at it and go, oh boy, that's a worst case scenario. What that one did, as far as I'm concerned, it sort of reinforced what I had already suspected, where I came in and I did my analysis and I saw that we had a negatively tilted trough coming in. And I knew historically that those are associated with significant tornado events in Alberta. And I looked at the resemblance of the surface pattern to Pine Lake with the hangback, cold front into the foothills. And then there was the drought going on in southeastern Alberta. And I thought, wow, there's an uncanny similarity here. And earlier runs of that model in particular, did not have a scenario like that playing out at all. And it was the 12 Zulu NAM model, the 3K NAM. I know it's at the edge of the domain region, but it sort of reinforced a little bit what I had suspected already. So I think, to put it another way, I had gotten 95% of the way there, but none of the model guidance was suggesting that what I was worried about was going to happen. And then when this came in, it was sort of like, oh, okay, they're flagging something significant to the north of Calgary. And that was the area I was worried about already. So I didn't put a lot of stock into it, but it sort of flagged something that I was already concerned about. It was sort of, helping me get the contours of the whole event as it unfolded.
Okay, great. Thank you. So I guess for the interest of time, it's 1:40, so we should probably move on. Thanks again, Eric. That was very good.
Yeah, you're very welcome. Thanks, John.
So if you can unshare your screen, please, and we can get, I guess, Dave Sills as the next speaker. His presentation is the detection and prediction of recent extreme thunderstorm events in Canada.
All right, I think I'm getting there. Let's see. How's it look, John?
Very good. You're good to go, Dave.
Okay, great. Thanks, John. And so that talking about the detection and prediction of extreme thunderstorm events is something I've been thinking about for about 10 years or so, mostly after that first event on there, the Toronto flood in 2013. And so this talk is basically put together to try to provoke some thought and hopefully even some action. So just looking at severe convective storm and their impacts, of the top 10 insured loss events due to disasters, now this is any kind of disaster, in Canada between 2004 and 2023, severe convective storms account for more than half, and those are the ones in red on that list. And more than half of the loss amounts too. So over 6 billion in insured losses, and likely as much in uninsured losses, and like we heard earlier this morning, maybe 2 or 3 times as much as that. And these include thunderstorm-related flooding events, damaging hail events, tornadoes, downburst events. And just to add to the impacts that not just financial, but the 2022 derecho, which also had 4 tornadoes with it, also resulted in 16 fatalities and at least 12 injuries. So, it's not just financial, of course. There's also, you have to think about the human impacts as far as casualties. So extreme storms, what are we talking about here? These are thunderstorm-related events that either have extreme impacts or climatologically extreme, either their season or intensity, that kind of thing, or their location. So I'm just going to consider 4 recent extreme events. That again, the 2013 Toronto flash flood, which is number 5 on that list. The 2020 Calgary hailstorm, which is number 4 on that list. The 2022 Ontario Quebec derecho was number 3 on that list. And then the event we just heard about, the 2023 Didsbury, Alberta, Ontario, which is, the rating at EF4 makes it an extreme event. So in each case, there were extreme impacts or intensity with these events that were not anticipated or forecast, or recognized in real time sometimes. So there are detectability issues too. And I'm not trying to criticize forecasters in this talk. They have the tools that are available to them. This is more about that information that comes into forecasters and what they can use and what's reasonable for them to be able to assess. And unlike severe storms, extreme storms have low predictability. So that means there's increased risk. And we'll get into that in a minute. So start with flash flooding. This is that Toronto flash flood case, so number 5 on that list. And this was a fairly typical summer day. It was 8th of July in southern Ontario. Afternoon thunderstorms were forecast. There was a special weather statement out for 30 to 40 millimeters of rainfall in that area that you see north of Toronto. In the Barrie area, you can see that as of 18Z or 2 p.m. local, there were already some thunderstorms that have popped up. And what's in purple there are the lake breeze fronts, so the Lake Ontario lake breeze front and the Lake Simcoe lake breeze fronts. And those will be important coming up. Mesoscale boundaries intersected here and provided an anchor for the convection. So you've got that the magenta lake breeze front, and then you've got an outflow boundary from that convection that was near Barrie. Go ahead another hour to 20 UTC, and the storm cluster is intensified, and because of that anchor at the intersection point, it's actually changed direction from heading southeast to directly south and into the most populated area of Canada. And you know, the next hour, 21 UTC, there's a flash flood disaster at this point. You can see the huge reflectivity zone right over Toronto. And it's so there's this disaster unfolding, and at that point, no warning was issued, and it was issued shortly after, but really too late. And I don't believe, talking to the forecasters, that there was much awareness that this was happening either, aside from what was coming through on social media. And that's where we'll go in a second here. So as far as the NWP, really provided no indication of the potential for 138 millimeters of accumulation in Toronto or anywhere nearby. You can see a couple examples off to the side there. In fact, they tried rerunning this case with the 250 meter HRDPS, and even after tuning and trying this and that, they just could not get any amounts anywhere near 138 millimeters. It's more like 50 millimeters. The forecaster conceptual models of the synoptic scale for flood potential really didn't apply in this case. It was the mesoscale processes at work that were really important. The critical piece to this was a thunderstorm outflow interaction with the lake breeze front. The first indications of anything potentially catastrophic happening were from social media. And again, the extent of the disaster was not apparent until hours after it had occurred. Next event, damaging hail. And I guess this was mentioned as well earlier today. This is the 13th of June, 2020 Calgary hailstorm, number 4 on the list, where we've got golf ball to baseball size, maybe even larger, 5 to 10 centimeter hail, driven by downburst winds. And you can see some of the photos of hail off to the side there. I'm borrowing a lot from Julian Brimlow and Sudesh Boudou's talk from Environment Canada for some of these images. There were copious amounts of large hail accompanied by heavy rain. And so in addition to the damaging hail, there was also widespread urban flooding, extensive crop damage from the large amounts of hail. The main losses were due to home roofing and siding damage and vehicle damage. And you can see examples of that on the side there, just vehicles being totaled, and look at the siding on the house there. That's extreme hail damage, basically. Again, we're looking at how this was predicted. Operational NWP doesn't yet explicitly indicate hail sizes. We could see from the talk earlier that this is coming, but at the moment it's not there. So basically, NWP is giving you conditions that can lead to hailstorms, and as you saw from Cameron's talk this morning, we're still learning more about that. The morning of, forecasters put the main hail risk well east of Calgary. So you can see in the outlook here issued by Environment and Climate Change Canada that morning, that orange area, which is their severe area, is east of the circled area where the storm occurred. And notice that the category extreme that they could have used was not used. Radar didn't indicate typical large hail producing supercell thunderstorms. It was some kind of multi-cell supercell hybrid. So it wasn't clear, even looking at radar. The first indications of potentially catastrophic hailfall was again from social media. And the extent of the disaster was not apparent again until hours after. Let's go to downburst. So we're talking about the 2022 derecho here. And NTP and myself, we spent months cataloging all the damage from this and doing the analysis. Continuous damage path near 1,000 kilometers long, max width near 100 meters. Several downbursts and 2 tornadoes caused EF2 damage, and we're talking about 195 kilometer an hour gusts. Because of where it was located in the Windsor to Quebec City corridor, it impacted 41% of Canada's population. Just a huge impact. And Ottawa was particularly hard hit with this event. We're up to 16 fatalities now. That's been updated based on my discussions with the coroner's office in Ontario. And we're still trying to find out about more injuries. What we know about at this point, there are 12 injuries, but usually the injuries far outnumber the fatalities. So we know we're low there. It's the deadliest derecho in Canadian history and the most thunderstorm related fatalities since the Pine Lake tornado in 2000. Some issues for detection. This is a map of all of the wind speeds that were recorded at airport or NAVCAN stations along the path of the storm. And you can see that there are some higher values like 110 kilometers per hour measured at Boutonville, 120 in Ottawa, 147 at Kitchener. When I went to get the data, the high resolution data from NAVCAN for this, it was apparent that there were some problems. First, the fact that the sonic anemometers are used is a bit of a problem because when there's hail and rain accompanying the high winds, those anemometers don't work so well, and the signal quality goes down. And because the signal quality goes down, you tend to start losing data. The example in the graph there is Boutonville, which recorded 110 kilometers per hour, but you can see in blue there, the peak winds cut out for the big main part of the storm. And again, that's because of the low signal quality with the sonic anemometer there. With the YKF or Kitchener 147 kilometer gust, I recovered that. It was again lost, or not completely lost, but it was downgraded and wasn't released initially. It was 131 kilometers an hour initially, but I went back through the data, and again, because of the signal quality of sonic anemometer, this was tossed out, but it was a good observation, so that's how we get 147. It was a good thing that it recorded at least 131 because that's what triggered the extreme thunderstorm warning on this day, which likely saved a bunch of lives. Another problem, if you look at Ottawa, you see 120 there. The power went out when the tornado hit the power grid in that area, and so the station communications went down. When they came back up, it had missed the main gust, and the 120 was the highest it got, and there was no plan to recover that data that had been lost, which I'm sure was just sitting on the logger, but then got written over. So we have some problems with detection of the highest winds with this kind of a storm. And then as far as prediction, the NWP pretty much failed miserably for this kind of storm. And again, it's likely because this is an outflow-driven storm. Microphysics is very important for that, and the models just weren't handling that well. You can see the HRDPS, top left there, valid at 18Z, and where Ottawa was getting hit hard, had nothing. The American model, the HREF is the ensemble model there, had nothing there. The outlook that was issued around 11:30 that morning, and the MCS had already started going across the area at that point, just had a couple areas with a moderate threat. I mean, they did mention winds to 100 kilometers an hour and maybe a tornado, but certainly not anything extreme. Let's go to the tornado. Didsbury tornado, you just heard about, and developed and tracked 15 kilometers between Didsbury and Carstairs. Thankfully, it didn't hit either one of those towns. Max path width of 620 meters. Connell went over all of the things that it destroyed, including lofting a 10,000 kilometer combine. So we're talking about some serious destruction here. The only injury, thankfully, was actually from a first responder. So because the warnings got out, people had it on their cell phones, they managed to get to safety, and no one was hurt, let alone killed in this event, which is pretty incredible.
1 minute, Dave, 1 minute.
Okay, thanks. Some of the first indications of the tornado were from social media posts. Again, extent of the damage not known later. The forecast with the outlook looks pretty good, but again, no extreme category used. So just how do we improve detectability? Social media is obviously an important source of extreme weather reports. We need better ways to extract that signal from the noise, maybe kind of reimagine CanWarn as a group of people that helps us pull the signal from that noise. We do that with NTP to a certain extent, actually. We need to revisit the decision to use sonic anemometers for the reason I gave. We need to work with NAVCAN to develop protocols for getting that high wind data, even when the power was lost temporarily. And we really need a high density, extreme weather capable monitoring network in and around highly urban areas around Canada, where the extreme impacts are more likely. So we have a better ability to detect key mesoscale processes as well. As far as predictability, first thing we need is high quality, long-term event-based climatologies. So everybody's aware, forecasters are aware of when things happen, where, how intense they typically are. I mentioned microphysics. We need better NWP microphysics to be able to accurately forecast outflow boundaries and their interactions and outflow-driven MCSs. We need to improve the ability to simulate and evaluate high-impact outliers in high-resolution NWP systems. And outlooks and alerts need to be conditioned on urban impact potential. I don't think that's the case right now. Just to summarize, Canada's experiencing increasing extreme impacts related to severe convective storms. More than meteorological factors at play here, of course, the impacts are due to other things like expanding city boundaries and so on. But we have little ability to detect extreme thunderstorms in real time. Social media is often the first sign of any unfolding disaster. We also have little ability to predict extreme thunderstorms, the impact or the intensity, even just hours before the event occurs. There are actions that we can take now to improve detection and prediction before the next extreme thunderstorm occurs. Thanks.
Great, thank you very much, Dave. We're a little bit over time, so I don't know if there is one question I guess we can, I could pose to you, Dave, if you don't mind.
Yeah, sure.
So high density weather network around urban areas in quotation. So I guess more stations or more frequent updates is the question.
Yeah, I mean, we've known from research that we need 1 minute data. We need stations with 10 to 20 kilometer baselines in between them. But the idea is just to be able to detect that an extreme event is either going to hit an urban impact, or sorry, an urban area, or is impacting an urban area. And at the moment, we just don't have that.
The old school anemometers seem to be the way to go these days too, right? Yeah. I guess the other thing, like another follow-on question was for radar, would you think something along the lines of the TDWR stations like the US has, like the like the terminal, like the airport type terminal radars?
Yeah, those radar stations, they update every minute, but they're C-band, so they have attenuation problems and they're limited range. They're basically for the airports. I mean, they come in handy because they have such high frequency. But I understand that Environment Canada radar scientists are trying to get an extra scan at low levels, at least, inserted into the strategy so that we have something every 3 minutes instead of 6. That would be a huge advantage as well.
Great. Okay, thank you. Thanks, Dave. Great talk. Yeah, so we can get, I guess, Daniel Butt is next in line. Maybe Daniel, if you can start sharing. So Daniel's talk is tornado analysis using artificial intelligence and treefall patterns.
You see my screen?
Yeah, you're good to go.
Perfect. Okay, so yes, like you said, I'm going to be presenting on tornado analysis using artificial intelligence and treefall patterns. Yeah, and so I'm a researcher with the Northern Tornadoes Project. Just thought I'd mention quickly, though, that I'm actually a software engineering PhD student. I'm not a meteorologist, so if I make a meteorological mistake, feel free to correct me, I suppose. So as was previously mentioned, the Northern Tornadoes Project has the goal of capturing all tornadoes that occur in Canada. And so as of the time of creating this presentation, from 2017, I believe, we found over 700 tornadoes. However, what we're finding is that approximately 50% of these tornadoes occur in areas with less than 1 person per squared kilometer. And so as a result, often the only thing that these tornadoes hit are trees. And so as opposed to usually like we'd rate the intensity of a tornado based off building damage or damaged structures, instead in these cases, we have to rate it based off the trees. And so how do we actually do that? And so there are two primary methods that we utilize. The first one is looking at the percentage of trees that have been downed in a given fixed size area, or area that's relative to the size or the maximum width of the tornado. And the second method is to use treefall patterns. So effectively looking at like a transect perpendicular to the tornado path, and then we look at specific patterns that it can create, and we try to match those patterns using simulations that I'll talk about later to try to estimate a wind speed from there. But in either case, we effectively need to know where all the trees are that were downed by the tornado. And in the case of treefall pattern matching, we need to know the actual treefall directions. And so in order to accomplish this, the Northern Tornadoes Project hires a company to collect aerial imagery for us. So they fly a plane and we collect a large-scale aerial imagery of the whole tornado track. That's about 5 centimeters by 5 centimeters per pixel. However, often there are tens of thousands, if not hundreds of thousands of trees that are downed in a single event. And so manually picking out all these trees and determining their directions would be very time consuming and tedious. And so we had the goal of creating an automated artificial intelligence deep learning model that can take in an aerial photo of the fallen trees, automatically extract the trees themselves by fitting lines to them, or we call it tagging the tree, and then automatically determine area averaged tree fall directions. And so a bit more about how this works. So first we have a semantic segmentation model that classifies each pixel in the images as having either being a part of a tree that's fallen or not being part of a tree that's fallen to create a mask like you see in the middle there. And then we have a second model that tries to fit lines to this mask. And so our first model is about 95% accurate for picking out the trees, and then about 80% accurate for fitting lines to the mask itself. And so to give you kind of a high level overview, here's part of a tornado track on the left, and then you can see highlighted on the right all the trees that were detected. And so you can kind of imagine if you had to do this manually, it would take a really long time. I think there are over 20,000 trees in this image alone. Then once we have a tagged tree, we can extend a box out around that tree and rotate that box so that it's horizontal, so that each image is uniform. And then we take this horizontally rotated tree box and we put it into a second convolutionary neural network that classifies it as having fallen to the left or the right or inconclusive, denoting that it thinks that there isn't, like this isn't actually an image of a tree. And then our prediction of the left or right plus the original orientation can be utilized to get a tree fall vector. And so then once we have all the tree fall vectors, we can then start to create area average tree fall directions over a specific area that gives us a tree fall map. And so to give you a high level overview of this, this is the Lac Gus Quebec tornado that occurred in 2018. And so if this was to be manually done, you would create a map like the one you see on the right there, and it would take a matter of weeks versus our automated analysis using the automated models that I've described gives you something very similar, but it takes more like a matter of hours to perform. And so then coming back to tree fall pattern matching, once we actually have the tree fall vectors, if you again take a transect of the actual tornado path, which is the red box you see on the left, we can then slice that box up to get area averaged tree fall directions to get an observed pattern like you see in the middle. And then we can simulate vortexes moving over the same area in the same direction as the tornado. And if the simulated vortex generates a similar pattern to the observed pattern, then we can say that how well it matches is proportional to how well the simulated vortex matches the observed vortex, the actual underlying vortex. And this in conjunction, if we know the critical tree failure speed, or effectively what wind speed it needs on average to knock over the trees, we can utilize this to get a maximum velocity estimate of the tornado. And so a bit about the model that we're using. It's a pretty simple two-dimensional model where at any point in the vortex is the sum of the radial, tangential, and displacement or translational speeds. And so the actual input parameters, we specify the maximum radial velocity, maximum tangential velocity, the displacement of translational velocity, which to simplify things here is just in a positive y direction. The critical tree failure speed, again, what speed on average trees are going to fail. And then things like the radius of maximum velocity. So at what radius is the vortex? Is the wind speed maximized? And so we're assuming a pretty simple single core vortex here. And so once we match these patterns, the idea is we can extract things like the maximum wind speed and also things like swirl ratio or the ratio of the tangential to radial velocity. And so there are a few different models we're using, such as the Ranking, Baker-Sterling, Burgers-Rott, and Sullivan models. And what these models effectively specify are profiles that tell you as a ratio of your radial distance from the center to your maximum radius of maximum velocity, what is the velocity to maximum velocity? So for the radial or tangential to the maximum radial or maximum tangential velocities. And so again, they're maximized when the radius is equal to the radius of maximum wind speed, as kind of the name implies. And so if I kind of give you a simulation here, if I simulate a vortex moving over a forest, you can see it knock down the trees and you create tree fall vectors. And so we're assuming that the trees are going to fail when the velocity is equal to the critical tree failure speed. And if you look at each horizontal row, you notice that the pattern you create is pretty much the same. And it's because the trees are failing in the same location around the vortex. And so we can actually analytically calculate this of where in our vortex do the trees fail by solving for when the velocity is equal to the critical tree velocity and then sampling at the first encountered location where this is true. And then if we discretely sample, we can create the pattern like you see at the bottom there. And what we found is that there are about 4 main types of patterns that you both observe in the actual tree fall patterns, but also that the model can simulate. And these can be classified based off of whether or not the trees fail inside or outside the radius of maximum velocity, denoted by inner or outer. And then there are some combinational ones, such as inner outer or outer inner outer. And so usually for lower wind speeds, you tend to see inner patterns where the trees are failing near the back of the inside the radius of maximum wind speed. Versus for stronger tornadoes, you tend to get outer patterns where they actually converge going against the translation of the vortex, failing outside the radius of maximum wind speed, as you see in the top left there. And so we've designed special software that will allow you to place a transect and move it along the actual vector field created from the artificial intelligence models. And in real time, as you adjust the transect, you can see the pattern that's being created, and you try to adjust it so that you can find a pattern that's similar to the ones that I just showed in order to give the most reliable and accurate results. And so as a kind of concrete example for the Alonza, Manitoba tornado that was rated EF4, we picked 6 different transects of this area. And then we used the Rankine and Baker-Stirling models. We compared the best matches between our simulated vortices and the observed treefall patterns and the simulated patterns. And what we found is that we got pretty consistent results to what we were expecting, where the treefall pattern matching estimated about lower bound EF4, which gives kind of a conservative estimate of the actual EF4 rating that the Alonza tornado had. And so this kind of served as a validation point for us that this method might work for future tornadoes. And so in conclusion, we've designed a model that can automatically detect fallen trees and their tree fall directions in large-scale aerial imagery. The detected trees and tree fall directions can be utilized to help estimate maximum wind speeds caused by a tornado that occurs in forests. And in the future, we might end up re-rating or at least using this tool to help assess maximum wind speeds of tornadoes. And if you're interested more about the machine learning models, we have a paper that you can read. So that's it for me. Thanks for listening.
Great, excellent talk, Daniel. Interesting, very interesting stuff. Very, very cool.
Thank you.
Okay, so we do have some time for questions if there are any. Let me see if let's see if I can figure out which ones are more recent than others. Okay, I don't see any specific questions. I don't know if anybody else here on the Zoom has questions. Dave or Connell, anybody has questions? Nope.
I'll ask a quick question. That's kind of a leading question though, but have you applied this to any other tornadoes that we have tree data for through the Northern Tornadoes Project work?
Yes, so we're actually in the process of re-rating, reassessing about 18 different tornadoes that we've captured large-scale aerial imagery for that were originally rated EF2, which is about as high as we can rate it based off of kind of previous methods. And so currently, this new method of treefall patterns is indicating that some of these tornadoes might actually have been EF3 or EF4.
There's another question just came through. So in the model for falling trees, is the soil moisture and tree health or type of trees taken into account at all? I guess that would sort of impact tree fall patterns and how many trees fall and where they fall and stuff like that.
Yeah, absolutely. So one of the biggest, kind of most challenging parts of this model is trying to estimate the critical tree failure speed, or like along the transect, what's the average speed that the trees are going to fail at. And so our current models, that I didn't get too much into detail here, but we have geotechnical engineers and kind of tree experts working on is looking at all those different factors of tree species and soil types and the size and shape and everything, all those different characteristics of the trees and the soil, to try to get a good estimate for at what speed on average the trees are going to fail.
Yeah, very good. Yeah, I know there's Tim Newsom. I think he's part of the team there, right? He's sort of the team, or the tree guy that's in part of NTP work. So that's good. I'm sure he's involved. Okay, great. Thanks again. Excellent talk. You can
Thank you.
stop sharing for now, and then so we can move on. I guess Lesley Elliott's the next speaker, and her talk is called "Downburst Damage Assessments in Canadian Forests." So can you on with the Treefalls?
Okay, can you see my screen there?
Yeah, you're good to go, Lesley. Good stuff.
Okay, so I am with the Northern Tornadoes Project. As John mentioned, along with Aaron Jaffe and Dave Sills, we've been working on assessing downburst damage in Canadian forests. So a few people have talked about NTP already today. I'll give a quick intro here. We study tornado occurrence in Canada with the goal of assessing true tornado risk. We put forth a lot of effort to detecting every tornado every year. This includes investigating witness and damage reports, completing damage surveys across the country. That could be a ground survey, drone survey, or arranging for aircraft surveys. We also complete satellite imagery review across the country. This could be where damage has been reported along a storm track of interest, as well as in the off-season, we complete a systematic satellite imagery review across the country looking for missed events or signs of older tree damage. Much to the chagrin of many people who report damage after a storm, not every storm produces a tornado. We actually find a lot of our investigations confirm that damage that gets reported is actually from downbursts. So what is a downburst? When strong downdraft winds descend from a thunderstorm towards the surface, hit the ground and spread out. Damage from a downburst can be on par with a weak tornado. Downbursts have been studied for decades. This diagram here on the right from Fujita and Wakimoto describes the various scales of downburst damage. At the lowest end there, we see the burst swaths that make up a downburst on the scale of the hundreds of meters. A microburst is a smaller downburst with a smaller impact area of less than 4 by 4 kilometers. And then we get higher up into downbursts along the 10-kilometer scales, downburst clusters of 100 kilometers. And at the very top, we look at families of downburst clusters. The scale of a derecho is sort of based on the size of these families of downburst clusters. As I mentioned, we do document a lot of events at NTP that are downburst events. We have over 400 events in our current database going back to 2017 for downbursts. Dave and several people have already mentioned that at the extreme end of this would be the May 22 derecho in Southern Ontario and Quebec, where we had 16 fatalities, at least 12 injuries, and over $1.2 billion in insured losses. There were 5 tornadoes recorded with that derecho, but the vast majority of the impacts were felt because of damage from downburst winds. And as I mentioned, we do complete a systematic satellite imagery review, and we have documented, or at least marked, the locations of hundreds of older downburst events that are awaiting documentation and assessment. In the long term, with this data that we're collecting, we'll have the ability to create a Canadian downburst climatology, but to do that, we need to be able to accurately and consistently rate downburst forest damage. On the right here is just a photo from the derecho in Eastern Ontario. So overall, how do we rate wind damage? We use the enhanced Fujita scale. This is the standard for assessing wind damage. This applies to tornado damage as well as downburst damage and more. On the right there, you can see the different levels, EF0 up to EF5, and the wind speeds associated with that. There are 31 damage indicators, or DIs, in the Canadian implementation of the EF scale. 30 of those are structural, and only one is natural, which is trees. For each of the DIs, there is a degree of damage that ranges from minor to total destruction. And when we know we've had a tornado or a downburst that does not impact any official DIs, it's an assigned an EF0 default rating. Here's an example of how we would use the EF scale for structural damage. We have a barn here that was damaged in a downburst in 2019 in Eastern Ontario. You can see that there is a major loss of roof panels of more than 20%, but we don't see a significant uplift or collapse of the roof structure. So this would fall in DOD4. Engineers assess this building as having an expected wind speed for that damage of 145 kilometers an hour, which gives us a rating of EF1. Here's a look at the tree DI table for the Canadian EF scale. You can see the damage described ranges from minor, which would be broken branches, to significant, with most trees snapped or uprooted, and possible denuded or debarked trees. The photos on the right here show the range that could be seen in damage, just a small little branch broken at the top. And at the bottom there, an area of significant tree damage. That's both of those photos are from the tornado in Rockdale, actinolite in 2022. So as you can see, for DOD3 and up, there's a mention of a percentage of trees down. So that requires us to look at a specific area to know what the estimated ratio of trees impacted is. And how do we know what area to use? We needed to develop a methodology where we used a scalable box to assess tornado damage in the early years of NTP. So we are using this to assess damage in forests that is beyond just broken branches. We're particularly looking for damage that we know is DOD4 and above. Our priority in early years of NTP was dealing with tornadoes at the time. So this applies to tornadoes. The scalable box is based on the max width of the tornado damage path. So you have a narrower tornado, you'll have a smaller box. A wider tornado will have a wider box. Within that box, you assign a DOD based on the percentage of trees down, and this is aligned with the tornado center line. And to validate this, we reviewed cases where we had high resolution of forest damage, and in the vicinity where we also had structural damage that was investigated by NTP surveyors. So we tested this method and we determined that a box with sides equal to 50% of the max width was a reliable, consistent, accurate way to rate forest tornado damage. So this is now our standard practice when we are looking at imagery-based assessments, drone imagery, aircraft imagery, or satellite imagery. This is just an example of what this looks like on a satellite image. So I have a tornado damage path outlined there in red. The estimated max path width is marked on there as 440 meters. When I apply my 50% box with each side of 220 meters, we can see that in that box, we have over 80% trees are down. This equates to a level DOD6. In this particular area, we know we have shallow soils, so we skew to the lower bound wind speed of 190 kilometers an hour, and this gives us an EF2 rating. So the tree DI in Canada gets used a lot, and this is one of the main motivations for us for developing a scalable box for tornado damage as well as downburst damage. This is because of the fact that we have huge areas of Canada where we have very low population and very few structures to develop as to damage, as Daniel just mentioned. This is a satellite image of Canada where I have just drawn a rough outline of the heavily forested areas. And if we take a look at our events that have occurred during the NTP years, these are all the tornadoes that we have in our database that have occurred over land. We go from essentially Western Canada all the way to Eastern Canada, Southern Ontario, up to the southern portions of the territories. And if I break this down by the rating basis, so the damage within the path that was the worst, the orange icons are where we have used the scalable box method on tree damage. Purple icons are when we've rated the tornado based on structural or weak tree damage. And the yellow icons are for tornadoes that did not impact any official DIs. And you can see on the map here that within that heavily forested area, we heavily rely on that box method to rate our tornadoes. Similar for downbursts, kind of a similar distribution for the 400 events that we have in our current database, ranging from Western to Eastern Canada, Southern Ontario, back up to the southern portions of the territories. And if we break this down by rating basis, again, in that heavily forested area, we see a lot of the brown icons that will use the box method once we've finalized it. Some of these events already have preliminary ratings assigned. The orange icons are the downbursts that are rated based on structural damage that was encountered or weak tree damage. And as I mentioned, we have many, many events that are pending assessment. All of these events marked on the map here will be based on the box method for the tree DI when we get around to it. So we have a lot of work ahead of us. Be great if we had some really interested grad students who wanted to take this on. So when it comes to actually developing the box method, we know that the scalable box method for tornadoes is not going to work for downbursts. These two events are just too different. Tornadoes have a relatively long and narrow path with a clear length, width, and center line that's easy to identify. The widest Canadian tornado on record is Brooks Lake, which is just under 2.5 kilometers wide. For downbursts, there's a much bigger range of aspect ratios. Downburst widths are more on the scale of 1 kilometer up to tens of kilometers. The dimensions of a downburst are generally pretty difficult to define. And downbursts are often made up of smaller areas of damage. So attempting to assess both of the events with the exact same approach is going to end up greatly underestimating downburst intensity. So our work is underway now to develop the scalable box method for downburst assessments. First, we have to decide how we're going to identify the envelope of a downburst. We are using an oval at this time. It appears to be the best way to identify both the swath centerline, which would be the major axis, as well as the max width, which would be the minor axis. So here's an example of what this might look like in northwestern Ontario. A few years ago, we had a very large downburst occur. So this heavy red outline here is the extent of the visible damage seen during satellite imagery review. And within that area, I have a dotted line outlining just the strongest area of damage within the overall impact area. So this is about a 50-kilometer long swath. The max width at any given point was 16 kilometers. And when I draw my downburst envelope over that, we have it just slightly wider, just over 19 kilometers wide. The next step would be to test the various box sizes related to the max width. So that would be our scalable boxes. And we also will test fixed box sizes, which is something we also did when we validated the tornado box method. So an example of what this might look like here for a downburst area where I've already got the oval drawn in the Yukon from last summer. The current box sizes we're testing are 10% up to 25% of the max path width. And then we'll also test fixed box sizes from 100 meters up to 1,000 meters on each side. And finally, the sort of most difficult part of this, the sticking point for us right now, is we need to validate the box method with structural damage in the vicinity used as the truth data. We understand how structures fail much better than anything else. So we only have a fairly small sample size at this point where we have a good amount of information about structural damage within the downburst envelope, where we also have notable tree damage. So we have 14 cases and not all of them are ideal. So we're hoping that in 2024, we may get some new cases. And we also have the ability to perhaps look back into pre-NTP years and search out forest damage with hopefully some structural damage that has good information recorded. Here's one case where we do have structural damage within the downburst envelope that was investigated by NTP researchers. This was just where we had the Lac des Îles tornado in Saskatchewan, and then a downburst immediately following the end of that path. And we can see we have some EF1 damage documented there by surveyors.
Lesley, you have 1 minute?
Okay, I'm at the end here. So the summary for us here, we know that damaging downbursts occur across Canada every year. They bring a risk to life and property for Canadians. Rating wind damage in Canada requires a heavy reliance on the TDI of the EF scale for tornadoes and downbursts. NTP did successfully develop a scalable box method for assessing tornado forest damage. And we need a similar tool for assessing the downburst forest damage. So there's my references, and that's it.
Good stuff. Thank you, Lesley. Very good. I don't see any questions on the event Moby. I don't know if anybody else on the Zoom here has questions for Lesley at all, or. Okay, I hear none. I don't see any on the, once again, on event Moby. So it is 2:25, so I guess we should probably move along. Actually, it's right on time. So if we can get Brad to load up his talk. So Bradley Power is our last speaker for our session, and his talk is titled Update on the Meteorological Service of Canada's Convective Alert Modernization Project. And it looks like your slides are all set to go. I think you're good to go there, Bradley.
Right, just mic check. I think everybody can hear me. So,
Yep, you bet.
little box also. All right. Well, thanks, John. Appreciate the introduction here. My name is Brad Power, and I work for the Meteorological Service of Canada in the Major Projects Office. And I'm the project manager for the Convective Alert Modernization Project. But I really want to acknowledge that I'm really the spokesperson for this project, and we've got a great team of talented people behind us. Comprised of meteorologists, engineers, computer scientists, and other program experts. So I'm just the mouthpiece. So my talk today is really just a follow-up to the presentation I gave at last year's Congress, where I introduced some of the proposed changes we're looking to make to our summer convective warning products. So so today I'll just give a quick review of kind of the motivation behind the project and some of the changes we're planning to make. And then I'll go through some of the lessons we learned from an internal evaluation that we did last summer. And then we'll kind of conclude with going through what our next steps are moving forward. So our current warning system basically completely relies on predefined warning areas to indicate where a convective threat exists. And this most often leads to over-alerting populations that are not necessarily under threat. So what we really want to be able to do is, any kind of storm specific details are actually hand calculated by the forecasters through using a couple different types of tools. And the only way to be able to get that information into the alert is by typing it into the freeform discussion area. So a couple years back, we did a little bit of an internal analysis. And we found that there are a few opportunities for us to be able to improve our convective warning service. First off, forecasters have long been able to more precisely identify the areas under threat from a severe thunderstorm. However, we really haven't had a good vehicle to be able to clearly communicate that publicly. Secondly, though the warning signal goes out almost immediately with some very basic messages in form of like pre-translated phrases, or any storm-specific information is contained within the freeform text, which then must be manually translated by our translation services. This introduces, on average, about 2 minutes delay between when the public initially receives that signal that the warning has been issued and when the storm-specific details are available for the public consumption. Finally, like I alluded to earlier, all of the storm details are manually gathered by the forecaster through using a variety of tools. So there's definitely opportunities for us to be able to streamline the forecaster's workflow by integrating all those tools into a single tool, and also by integrating some geospatial data into that warning production process. So what we're doing is we are actually introducing time and georeference freeform polygons, which will allow our forecasters to more precisely define the warning threat area. This should significantly reduce our over alerting, our aerial over alerting, and this is in particular for areas that are upstream of the threat, so where the storms actually already passed through. This polygon, we will be using it within our dissemination platforms to better target where the warning notifications are being sent. But since how our platforms represent only a fraction of the ways that the public actually gets our warning information, we are also making that freeform polygon information available through our CAP CP files, in addition to our the forecast zones or the CLC codes that are currently in use. So this will allow for, some platforms to, catch up and use that information while not losing the ability to issue warnings as they stand right now. Within that CAP file, there is actually no limit to the number of vertices that will be going out. So the freeform polygon that the forecaster draws will be what you will see, what will be in that data. In addition, within the CAP files, we're also going to be including the threat location and the storm motion vector. And so through the streamlining the forecaster workflow, which we've been working pretty hard on here the last couple of years, we're actually able to gather storm-specific details about the storm as the forecaster is defining the warning polygon. These details can then be inserted into a pre-translated phrase template, which means that we can get that information out without it having to go through a manual translation process. And so that immediately that information will be available when the warning is issued to the public. We'll also allow the forecasters, the forecasters will still have the ability to add other details, other pertinent details into the warnings, into the freeform discussion if they need to. So one of the biggest changes that we're actually introducing with our with the service is really that we're going to allow our severe thunderstorm and tornado warnings to overlap in space and time. In our current system, those warnings cannot coexist over the same place and at the same time. This was basically done back in the, I want to say 90s-ish. It basically allowed us for simpler management of notifications being sent out to the public. However, as we move away from the predefined zones to be able to get the more precise definition of threat area, we're going to have to move away from this policy. And this creates some new challenges for our dissemination systems, particularly in scenarios where there are multiple threats that are in close proximity to one another. And, it gets even more interesting once you start looking at our broadcast and immediate messaging, and to a lesser extent, our wireless immediate messages. So from the evaluation that we did last summer, we did have our forecasters use the prototype system with real weather or real-time weather. And what we were able to find out was that on average, we're seeing about a 75% reduction in aerial over alerting. So that was a pretty big win. It was pretty easy to be able to go on based on smaller polygons versus the large freeform polygons. However, we did identify numerous scenarios where we were starting to introduce the risk of message over alerting. So this means where we'd be sending out too many notifications about a single threat. And, if there's one complaint that we get with Environment Canada is that a lot of notifications, people feel like we're spamming them if there are too many notifications coming from us. So this really becomes an issue because we're, it stems from us increasing the precision of the warnings. In the past, we could fit, or one forecast zone could envelop multiple storms, whereas with these freeform polygons, we can be much more precise about where the threat is within the area. So was that we found that Also, as a result of having more or smaller warnings, sometimes those warnings will actually merge together, or sometimes lines split apart into multiple alerts. And what we found is that in these situations, we have to carefully manage the notifications that are going out, because we're actually increasing the probability of there being multiple new warning messages for the same storm. So I'll go through quickly. We introduced two new workflows for the forecasters to be able to work through. So imagine in this kind of scenario, you've got two cells kind of bookending around Calgary, but they're starting to grow upscale into a line. So what the forecaster will do is they'll actually create a draft of warning over top of this. And what's we're basically doing is this workflow is going to allow the forecaster to explicitly tell the system they plan to combine these two alerts into one. And what this will do is allow our backend systems to create a relationship between the two warnings, so that people under the star don't get so the people underneath the star wind up getting an updated message rather than a new message. So what'll wind up happening is, as the forecaster issues these warnings, it'll merge into a single one, and people underneath that star will see an updated alert, whereas the people in Calgary, who were never initially under threat from those previous storms, will now see a new alert. Similarly, for splitting warnings, we've also created a workflow that will allow the forecaster to tell potentially slightly different stories about the same line of storms. So imagine if you've got a tail end Charlie kind of situation. What will wind up happening is you can split that particular portion of the alert off and let it go off and do on its own. But again, those people underneath that star will see a continued message, as opposed to seeing a new message when that split actually happens. So one of the other things that we ran into, a couple of the other issues that we ran into, came from actually the management of the warning. So the update cycles as these storms were actually moved through. There's two kind of effects that kind of show up from the slight changes to the storm motion vector, which could lead to some flip-flopping notifications to locations along the edges of the warnings. Just as people move in and out of those alerts. Now, these two examples that we have here, they're pretty exaggerated from what we saw during the evaluation last summer. However, these effects really aren't all that new, since the National Hurricane Center deals with these issues when they're issuing their hurricane track forecasts. The main difference with this, though, is that the issue is exacerbated by the timescales that convective warnings operate on, right? The storm tracks are updated, every 12 to 24 hours thereabouts. Whereas, these severe thunderstorm warnings are issued on or updated every, 15 to 20 minutes. So we really want to make sure that the public's not getting any confusing notifications. And basically, what this looks like is, we don't really want people moving in and out of the warnings. Now, we do have some technical solutions that are possible that we can implement on the dissemination side that would essentially create a little bit of a buffer and delay the ended notifications to allow for slight wobbling of the storm track. But we've decided to, in order to be able to maintain the flexibility that's needed in order to be able to deliver a responsive system, we really want to take advantage of the fact that forecasters are actually responsible for the update. So it's still manually decided when that update is actually coming. And so as such, we can actually, we're actually investigating some enhanced visual cueing during the drafting phase of the warnings, the warning production process, that will help forecasters identify situations where these issues may be occurring. So going forward, this summer again, we've decided that we're going to do another round of the real-time evaluation, along with some simulator sessions that are really going to help us assess the forecaster workflow, make sure that it's being optimized and that it actually integrates into the operational workflow in a sustainable manner. You know, there will be more alerts for the forecaster to be able to manage, and given the size of our area of responsibility, you know, in a convective outbreak situation, this could actually lead to some workload considerations we have to keep in mind. So we want to make sure that our workflow is as efficient as possible. We're also going to be gathering all the data that's generated during those evaluation activities, and we're going to be doing continuing our in-depth analysis into the changes we're considering to our warning service to make sure that we are actually improving our service. Right, you know, we're reducing aerial over alerting, but we also want to make sure that we're not increasing message over alerting in these situations. We'll also be continuing our collaboration with some of our key alerting partners, you know, to be able to ensure that the data that we're sending them is integrating into their systems seamlessly. And all this means is that we're also working towards a tentative implementation date of spring 2025. Now, the actual implementation date is conditional on you know, the results of a lot of our evaluation activities, because you know, we want to make sure that we're safeguarding our current service levels. So you know, in reality, we're breaking new ground with these freeform warning polygons, and as a result, you know, there's still lots of learning yet to be done. Still lots of testing that really needs to be done. We need, obviously, like I mentioned before, we need to validate that the changes we're making are actually improving our service. But we're also working not only to make sure that we're managing the notifications that we're sending out on our platforms are appropriate, but we want to also make sure that we're providing our partners with the information that's needed to be able to control the messaging on their platforms. And of course, of utmost importance to us is also ensuring the integrity of our alert ready system or of the alert ready system, and of course, you know, making sure that we're regarding that the public is actually going to respond to those messages, right? Because if we're spamming them too much with them, they may start to ignore them. So we want to make sure that we're not over messaging them.
Hey, Brad, that's the 15-minute mark. So
okay, I've got the summary message. That's about it here. So, okay, so last quick messages. Work is underway to be able to bring these freeform polygons to Canada. We're changing some of the longstanding warning policies. And, you know, though we've already addressed many challenges, there's still more to come, and we're going to be carefully assessing those to make sure that they're good. So, but that said, progress is being made every day, and hopefully be good to go in 2025. Hopefully, we're working towards that. So leave it open for any questions.
great, thanks again. That's a very good update. So I'm glad it's plugging along. It's good to see. So there are a few questions online here. So the first one, this looks more similar to what the NWS is doing. Is that correct? And how can the public get notified online, I guess, is the question.
Yeah, this is very similar to what the NWS is doing. There are some slight differences. Their current warning paradigm allows them to issue you know, freeform polygons, but they can't actually move those polygons with the threat. So that is something that they're hoping to address with their Tiny TIM, or the Tiny Threats in Motion project. So yes, it is fairly similar to that, but we are in communication with the NWS leads there, and we're sharing lessons learned between these two projects.
Okay, great. So just I guess there's more just popped up. So so one is I'm a bit confused with how the alert updating will work. So don't you want forecasters to predict where the storms will go in the next hour or so and not constantly update the storm track at each new radar image cycle?
Yeah, so that's what the alerts, the polygons are actually targeted to go downstream from where the storm currently is. So you're only ever alerting downstream from where the storm is actually moving. So are they expected to update with every radar cycle? No, no, that's very, very workload intensive. And if you're monitoring 5 radars, there's no way that you could do that with all of the storms that are going on with that. So like I said, the forecasters already update the alerts and move the warning areas further downstream from those storms. This system will just make it a little bit more consistent in how far downstream they're actually issuing it.
Okay, great. Well, I'll just fire up a couple more, I guess. This is really great. It's needed as soon as possible. Will warning ended messages be generated for locations where the warning is no longer in effect?
Yes, they will. Within the CAP messages, there is going to be a block for new area, continued area, and ended area. So there will be areas that are back and behind. Now, I'm not sure what you mean by a warning ended message, because Environment Canada does issue a warning ended message for all their alerts. So I'm not sure whether you were talking about like through the alert ready system that you're expecting to see the all clear, or whether that's through basically an app or something of that sort.
Yeah, good question. I'm not sure. They don't really specify, so.
Yeah.
Okay, maybe one more. Let's see. Great talk. I may have missed it, but what will the alerting also include geographical depiction of the polygons to the public? So I don't know if that would appear on the alert page or where that would appear.
Yeah, yes, on our the main warning page on the Environment Canada website, that will be these warning polygons will be visible there. And of course, there is the functionality to underlay the radar data underneath that as well. So that will be displayed on the Environment Canada website. And of course, I'm assuming multiple apps, which we haven't talked to Radar Scope ourselves, but they do access our CAP files, and they will be able to see that freeform polygon in there.
Okay, great. Yeah, the last one was just they were wondering what the planned date for operationalize when it's going to start working. I guess you mentioned the spring of 2025, but I guess that could be delayed depending on how things go.
Yeah. So the spring 2025 is our tentative target date. However, like I said, we do have to make sure that we're not increasing the notifications that are being sent out to people, and that we're actually safeguarding our current our service level, or improving our current service level at the very least. So.
Okay, great. Well, thanks again for the great talk and lots of good questions. So I think that's sort of it's probably the end of our session. So I guess that's the end of our severe extreme convective storms session. So I just got, on behalf of myself and Dave Sills, just thank all the speakers again for the excellent talks, especially Cameron Nixon for taking the time, who started our session with the opening talk, which is really fascinating stuff with the hail. Thanks to the audience for attending. So we appreciate everybody's attending our session. And I think the next sessions start at 3:55 Eastern Daylight Time. So it's coming up fast and furious, I guess. And don't forget about public talk tonight at 6 p.m. Eastern for those who are able to attend. So thanks again, everybody, for joining our session, and enjoy the rest of the conference.